Just to so welcome everyone to the class on smart materials and structures. Good morning to each and all. In the last class, what we were dealing, can you just brief out quickly within 2 seconds? Mohan Ambal?
Yes, ma'am. Shape memory alloy, like history on shape
Yeah.
memory alloy and introduction to shape memory alloy and how they
Okay.
work, like that.
Okay. Anything else apart from that? We also spoke about a particular methodology, what we have to solve, what we have to use in order to solve the problems associated to harmonic excitation of the module 1. So we dealt with the methodology of the problem, what we have to use to solve the problems related to Euler-Bernoulli model. And then we started with the shape memory alloys. We started speaking about its history, how does it originated, how it works exactly, what are its classifications, right? So we spoke about the introduction, how the deformation comes into picture when heating, when cooled back, how it goes back to its original position. So we spoke about their working nature. Then we spoke about the phase transformation which come across during the austenite and martensite phase. So austenite phase is at the beginning. When you apply the temperature, it gets the required change. So when it is cooled down, it comes into the martensite phase. So we dealt related to that with two terminologies, what you have to be knowing: the twinned martensite and the detwinned martensite. So it is one step of heating and this is the second step of heating. Okay, so this we dealt about until here. I think we have to start up with the types of shape memory alloys which are in existence. So once you know what you mean by shape memory alloy, how does it work, and the phase transformation, you should be also very keen in which is the main classifications across our shape memory alloys. In this aspects, we have two main families, two huge bifurcation families under shape memory alloys. So one is purely based on copper alloy. The second one is purely based on the nickel alloy. Okay. So based on copper alloy, this was the beginning thing. So you had copper, aluminium, and nickel. So these three together made a good alloy combination under the classification of shape memory alloy. So one more sub classification under this family is copper, zinc, and aluminium. So both these combinations of alloys had a very narrow hysteresis loop. Hysteresis loop we had studied already at the time of understanding the ferroelectric nature of piezoelectric materials. So there we subjected the electrical field to see how the voltage is enhancing. Even after the removal of the electrical field, there was some spontaneous polarization, what we called, and then it stored some amount of polarization in it. We call that as a remnant polarization. And again, when the total electric field was zero, then it came to the coercive field. And all these things we have studied related to the piezo material. Similarly, even the shape memory alloy will be having an hysteresis loop. So it is a closed cycle. So it will start like this and again come back. So you will see the nature of the curve when heating and when cooling in case of shape memory alloy. But whereas in case of piezo, it was like application of the electrical field to see polarization is done, and at the removal of the electrical field you used to see how some amount of polarization is retained. So that used to give you a closed loop. Similarly here, for heating and cooling you will be having a very narrow hysteresis loop. And this hysteresis loop will show you the adaptability to store the memory in it. How was the structure at heating and how was the structure at cooling? So both these materials showed a good hysteresis loop of narrowed structure with the capability of having the memory capacity to come back when it is cooled. So this is one of the classification, and the other combination was totally on nickel based. So you have nickel based alloys. So one main familiar composition of alloy is nickel with titanium. So along with nickel and titanium, you have a third element of alloy. Okay, so that used to be used as a type of combination of dopants in order to see that it is having the required capabilities to regain its memory of the geometry once it is subjected to cooling. So in that way, nickel based alloy as a ternary element, and this was called to be represented by the letter X. So what differentiate you have to understand is most of all the SMA applications are based on nickel titanium alloys. So it has a third section where you have to add an ternary element. Okay, so most of all the applications are made up of nickel based alloys only. So when you compare with copper based shape memory alloys, nickel titanium alloy is more expensive because the titanium alloy itself is expensive, right? So this makes it to be more expensive. And one more thing is when you are operating, what happens is this nickel titanium alloys are expensive because it has to melt and produce the copper alloy. Okay, so when you try to synthesize these alloys and do actual shape memory effect, you'll come to know the pain how much it is in melting and regaining back its position. Okay, so but they are preferred for their corrosion resistance, but still this nickel titanium alloy is used because due to their important property which has resistance to corrosion. So resistance to corrosion will help you to use this alloy for a longer period of time. Apart from that, it is biocompatible. Main thing is it has to be biocompatible. Then you can use for any bio applications related to biomedical also sometimes if it is in need. And thirdly, other plus point is it has higher electrical resistivity, okay, for heating in actuator applications. So this again is relating to our piezo material. Okay, so it has high electrical resistivity for actuator applications. So depending upon the property or depending upon the application what you need, you can use this nickel based alloys not only for shape memory applications, even for the other applications like actuators. So one thing when we speak about the classification, you have to understand two things. You have two main families of alloys. One is of copper based and of nickel based. So copper based will show a very narrow hysteresis loop in comparison to the nickel based alloys, right? Both have the capability to regain back its memory, but still nickel based alloys are used for more than 90% of the new applications which are coming through shape memory alloys. That is due to some of the important properties because it is corrosive resistance, it is biocompatible, and it has a very good electrical resistivity with respect to even heating in case of actuator applications. So due to this, nickel is more familiar and used in a larger scale in compared to copper based alloys. So once the classification of two main families is clear, you should now understand what is the main characteristics of an shape memory alloy. Okay, so shape memory alloy, the name only it suggests it has a capability to regain the geometry because of the memory concept. And hence one of the characteristics of shape memory alloy will be nothing but the shape memory effect. Apart from that characteristics, it has one more characteristics which is called as super elastic effect. So all shape memory alloys, what you develop by mixing n number of alloys of either nickel based or copper based, both the families should have these two characteristics, which is the shape memory effect and the super elasticity effect. So now we'll start up with shape memory effect. So what do you mean by it? You know already the word itself will suggest, but still you should understand how the change within the alloy takes place from one phase to the other. So I have told you in the last class, it has mainly two phase. One is the austenitic phase, another one is the Martensic phase. So austenitic phase you will get when you are subjecting and heating cycle to it. So when you have got the required alignment, and later when it is cooled, it will come back to its original position. So that is nothing but Martensic phase, right? So shape memory effect here is based purely on the Martensic phase transformation, which takes place without any diffusion. So if you speak about diffusion, again diffusion has wide area of meaning with respect to physics as well as chemistry background. So here you are telling that the Martensic phase transformation takes place without any diffusion. Initially, when you have an alloy, when you subject to chemical reaction related to solid state kinetics or whatsoever, the molecules of the two alloy will diffuse together to form a new compound. And hence there will be some change in phase and you yield the result what you need as an output. But here in this case, the material will be able to come back to its position back without any diffusion. That one thing you have to understand. It is purely based on heating and cooling you get the required change in the material behavior, and hence Martensic phase transformation occurs as a result of either stress or temperature change. So stress might be due to mechanical loading and also due to the variation in the temperature. So when you speak about the shape memory effect, you should not always think that only due to heating or cooling it comes into picture with the change of phase. No, apart from temperature change, even the mechanical loading can get the required phase transformation in any shape memory alloy. So here now you can see a small diagram which representing the change of phases, right? So initially what happens is, suppose you have and shape memory alloy. You apply some mechanical loading to it. Here we are not applying temperature initially, you are subjecting to a mechanical loading. So the material gets deformed slightly. So once it is deformed, then you subject the shape memory alloy to a particular heating or at a particular temperature. So then what happens is the regular shape memory alloy now changes into the austenitic phase because there is a change in the heat which is passing from the deformed Martensic phase to that of austenitic phase. So once it has regained the position as required for a particular application, once the work is done, then you start subjecting cooling treatment. So when it is cooled, you can see that it will come back to the original position in which when it was deformed. And it will not be the same. You can see the arrangement of the molecules here. The first row is same, the second row is same, and the third row you have the variation here. See, here it has one molecule behind, and here whereas it is a small change. So minor change in the memory will come back, but you can say that around 90 to 95% of the memory can be regained by the cooling treatment. I told you initially also, it won't come back to 100% of its geometry, nearly 90 plus. So it depends upon again the combination of alloys what you are using for which specific application. So this will be the entire cycle of the shape memory alloys which will be showing the behavior related to shape memory effect. Okay, and similarly, super elasticity effect you have to understand. So, what do you mean by super elasticity? So, here I told that with irrespective of to what high temperature you are subjecting the shape memory alloy, it will come back to its original position. That means to say, even though you apply a very high amount of heat also to the shape memory alloy, it will not reach the plasticity state. It will be in elastic nature only because it can regain back its original position, and hence it is called as super elasticity effect. So if it has a shape memory effect and if doesn't have the characteristics of super elastic effect, then you cannot claim that the alloy what you have prepared is an shape memory alloy, right? Even though it has its memory concept in it to regain the geometry, if it is not elastic in nature, it won't be able to come back. It will reach the plasticity stage, right? And hence you should see that while playing with the alloy combinations with copper based and nickel based, you have to see that all the alloys are having super elasticity nature along with the memory concept in it. Then only it will be able to achieve super elasticity effect, because there are many materials which has the elastic state as well as the plasticity. So when you subject to certain load within particular range, it can deform and come back to original position. Suppose the viscous, or what we say the viscoelastic foam, if you synthesize the polymers of viscoelastic foam, it will be not rigid. So even though you apply some load, it can compress and come back to original position if the load subjected will lie within its elastic limit of expansion and contraction. But if the load what you're applying is above the limit of the viscosity, above the limit of that viscoelastic composite, then it cannot come back to original position. When compressed, it won't come back. Then you will say that this viscoelastic foam is not within the elastic limit. It has crossed and reached the plasticity. That happens in many materials. But in case of shape memory alloys, this is a very important property. Irrespective of the load what you apply, irrespective of the temperature, high heat treatment what you are doing, it will be having the capacity to come back to its original position. And hence we call this as super elasticity effect. So this is just a diagram to show how the phase transformation can be induced thermally. Okay, so this is the austenite phase which will be regular. So now what happens is you will reduce the temperature and finally it comes down to martensite phase. And again from martensite phase, if you increase the temperature, it comes back to the austenite phase. So this is the cycle which keeps on happening when you apply a specific loading. So you will be having a martensite phase of a specific shape memory alloy. You subject to mechanical loading, it gets deformed, and the deformed martensite will be heated to get the austenite phase, and the austenite phase, when it is cooled, it comes back to its martenized phase, which was in similar way before mechanical loading was subjected. So here one of the figure has to show the pure structure of the alloy, how it looked before loading. So once it is loaded, it is deformed. Before deformation, it will look similar to this. Okay, but since it is heated and cooled, it will be twinned martensite twice, right? Subjecting to heating and cooling, you will call that as a twinned martensite. But the structure will be almost similar to the initial position of the shape memory alloy. So this is just to make you understand the changes. Okay, so here the next diagram shows you the mechanical deformation, how it has been happening. And here you can see an loop here. So what is this loop called as? Anyone can guess and tell me after seeing here? How does it look like? You have studied piezo material also. If you see this loop, what does it shows you basically? Anyone in the class? How the diagram looks like? Hello?
Hysteresis loop.
Yes, good. So
Hysteresis
it has
loop.
the, yeah, right. So as I
Hysteresis
told
loop,
you,
ma'am.
yeah, Mohanambal. As I told you in piezoelectric material, you have a hysteresis loop. Similarly here, you will be having an hysteresis loop of little narrowed area in between. So it will be due to heating and cooling. So this is the heating curve and this is the cooling curve. Okay, so this shows you the variation in the structure of the alloy across different points of heating as well as the cooling. And this is just the image I have explained you already in the previous thing. Here it is the same concept. So we are correlating here the change of phase with respect to the hysteresis loop. So how it happens, I'll explain you one by one, stage by stage. Here you cannot understand which is first, which is second. So I just got a clear picture for you to understand how the steps goes on. So the step of the hysteresis loop starts from the origin. So towards your x it is the strain axis, okay, and towards your y it is the stress axis, and towards your z that will show you the variation in the temperature. So in case of hysteresis loop of shape memory alloys, you will be having three axes: strain, stress, and temperature. So the path followed by your shape memory alloy will start from the reference point. So from 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, and this goes on. So always the twinned martensite will show you the actual reference of the alloy, how it looks initially. Okay, so then it will start gets changed due to the subjection of heat, yeah, whatsoever. So now let us start with the explanation. So I have told you that it represents a stress, strain, and temperature space. The material starts from the reference configuration at zero stress. So when the material is here, the material does not have any stress or strain. Why? The material is not subjected to any temperature. At this point, stress will be zero, strain will be zero, and temperature will be zero. And hence, it will not be having any induced stress or strain in it. So this is the first stage, right? So now the material start moving from 1 to 2. So you have a slope from 1 to 2. So what happens here? As it moves from 1 to 2, you have the variation in your stress value. So you can say when the shape memory alloy moves from 1 to 2, you have the variation in the stress because you are applying temperature to the shape memory alloy. Due to the enhancement in the stress, due to the enhancement in the temperature, the stress increases, right? So the stress increases and the material behavior is at first linearly elastic. So however, with respect to any temperature, it will be having the elastic behavior. So now 1 to 2 slope is over, right? So then apparently plastic deformation starts to develop the constant stress. I told you it is totally super elastic in nature. But when you're plotting a graph of three values, stress and strain, you need to know the value of strain also. So to know the value of strain, it has to reach some plasticity in it. So what we do is, so apparently the plastic deformation starts to develop nearly and constant stress. So here you will not be applying any heating. What you will do is first you initially at the first position you will heat, you will subject to some particular temperature heat treatment. So now the stress increases within the given shape memory alloy. So after that it will be held at the same temperature for some period of time. So that helps in developing the plasticity nature in the material to evaluate the amount of strain is induced in the material, because you if you keep on increasing the temperature directly without any soaking time or dwell time, you cannot understand what is happening within the material. So you have to retain some amount of constant temperature. Suppose if it is at room temperature here, you will increase the temperature to either 90 or 100 degrees Celsius. So due to increase in the temperature, the stress goes on increasing. Once it is 100 degrees Celsius, you will not still increase above. You will just maintain that temperature for some period of time. So there will be consistency in the value of the stress. The stress will not increase. But at this point, you can observe due to the heat treatment, some changes occur within the material and it evaluates the amount of strain induced within the given shape memory alloy. So this transverse movement of the path will show you the amount of strain induced in the given shape memory alloy. So this shows the plastic deformation which starts to develop at constant stress. I told you the stress here will be constant because you are not applying any you're not applying any temperature. The stress will be constant, only the strain will be induced. So you will come to know what is the amount of strain induced at constant stress. This happens only in plastic deformation because it is not coming back to its original position. It is retaining at that particular stress, right? And hence it is that plastic deformation condition where you evaluate the strain at constant stress. So this happens from the path 2 to 3. So once 2 to 3 is over, you will next go for the slope 3 to 4. So what happens in 3 to 4? The SMA deformation reaches the saturation and further increase of load leads to linear elastic branch. So now when it moves 3 to 4, it has reached the maximum stress value. Since it has reached the maximum stress value, the material here is deformed due to the stress for consistent increase in the temperature. Until here you will increase, from there it is a constant temperature which is there throughout, where you will measure the strain across the constant stress. So from 3 to 4 again you will increase the temperature, right? So due to this high temperature, so deformation comes into picture and there will be change in the structure of martensite, and hence we call it as detwinned martensite. And one thing you have to understand about that particular point, if you still increase the temperature, then the linear elastic branches gets formed. That means to say is this is the upper limit of the temperature the material can withstand. So above this there will be no increase in the stress. Okay, it will be in the elastic behavior. So it will come down. This shows you the elastic behavior of the material. So here it is a plastic deformation which comes into picture. So after 3 to 4, even though if you increase the stress, it will not increase. It comes back to elastic deformation of the material. Means it comes down. Irrespective of applying high temperature, it comes down, means it is coming down to the elastic behavior to regain its original position. And hence you will be able to understand which is the optimized temperature where you can get the highest stress level. So at that point, the twinning of the martensite phase comes into picture. So that point is called to be as detwinned martensite. So this is the thing which happens from the slope 3 to 4. So once you have reached the detwinning of the martensite, then it starts coming down due to its elastic behavior. So now the no temperature you can increase. So the temperature will be dropped, right? So then it gradually comes down. Okay, so the again detwinning of the martensite happens. First twinning will happen here. So this is a regular martensite phase, and now here detwinning will happen, and as a result, after the removal of the temperature, one more twinning will be here. So when at this stage, the strain will be totally zero because there is no increase in the temperature and the cooling part is coming. And as a result, the elastic deformation of the material is coming to regain its original position. Okay. So gradually you're not increasing, it comes down from 4 to 5, from 5 to 6, right? And totally here the temperature is almost to the room temperature. And from here it goes back to 7 to 1. From 7 to 1, it will be the original position of the shape memory alloy. How does it look like? So here what happens, from 7 to 1 you are increasing the temperature. So when you are increasing the temperature slightly, it could be due to temperature increase or mechanical loading. So that will result in the first twin of the martensite. So this process goes on. So when you subject to the mechanical loading initially, it is the first winning what you get. And after the increase in temperature and getting and consistent stress, and again you will increase the temperature until it reaches the saturation limit. So at that stage, the twinning of the martensite happens for the second time. So the second time twinned martensite phase will then come down gradually as the cooling cycle has started, right? And then it regains back its austenite phase. So this is how the change of phase takes place in shape memory alloy. So initially the stress and the strain and the temperature will be zero, right? So you will be just subjecting to the temperature your mechanical loading that results in the first twinning at the martensite in room temperature. Then you gradually increase, the stress increases. Once the stress is constant, you will stop the application of temperature increasing. So the same constant temperature. Suppose if it is 100 degrees Celsius, you will maintain the same 100 degrees Celsius, okay, until you get the required strain deformation in the plastic stage. So once it is done, then you will again increase the temperature until where the stress will be maximum. That you will not be knowing initially. So when you start increasing, it increases to some certain extent, then it start dropping down. Then you'll come to know which is the optimized stress the material can withstand. So at that point, the second winning of the martensite phase comes into picture. So from then onwards, you won't subject any temperature treatment. So it gradually comes down, comes down. The same D-twin martensite will cool down totally and reach other original position here. So where it will be the austenite phase. So this is how the loop goes on and on and on until you need the change of phase from martensite to austenite. So this is how it works. Hope it is clear. Do you want me to explain again? Is that clear?
Yes, ma'am.
Okay. So next, the same thing is explained here in theoretically. I have told with respect to the diagram. So when we were speaking about the shape memory effect. So in shape memory effect, we have two types. Okay, so one is one-way shape memory behavior. So what do you understand from one-way shape memory behavior? So here, the transformation to the desired shape occurs only upon heating. So you have the classification of the material which has two-way and one-way shape memory effect. So in one-way shape memory, the required transformation can occur when you subject to heating only. Okay, so the memory is with the austenite phase. So when you heat from room temperature, so first it will reach the austenite phase. So the concept of memory to regain back its position is in its austenite phase only. So this is called as an one-way effect. So here it is the austenite phase what you have with respect to the cooling. With respect to heating, you have just the austenite phase. So and the memory concept here will be related to the austenite phase only, and it is one way effect. It cannot come back. So this is one way shape memory effect. So next is the two-way shape memory effect. So what happens in two-way shape memory effect is the deformed shape is remembered during the cooling. In addition, the original shape being remembered during the heating. Means the capability of the material has two memory funda here. One is it will be in the regular room temperature. When it is subjected to heating, it gets the austenite phase. So that deformation which comes into the body due to heating, even that is remembered. And when it is cooled, right, the condition of the state of the material, even that is remembered. Means it has memory concept in both austenite and martensic phase, where it can go and come back, go and come back to and fro. Then the hysteresis loop will be closed because it has two-way shape memory effect. If it has a single shape, if it has a single way memory, what happens is it cannot regain back its original position. This will be the initial. Okay, so when heated, it can deform, but it won't be able to come back to the position back because it will not be having the memory when it in the cooling stage. If this is the regular wire of SMA, when you apply it to heat, it gets bended or it gets deformed, right? But it has to come back when cooling. To come back when cooling, it should have the memory effect in martensite phase also. Then only it can come back. If it does not have memory concept in martensite, then it is a one-way effect only. So it can regain the memory of the deformation shape only and not the memory of the original wire of the shape memory alloy. In this case, we call as one-way effect. But whereas in case of two-way, it can deform and come back to original position because it will be having the memory concept in both austenite and the martensitic phase. So this is the difference between two-way shape memory and one-way shape memory. Apart from that, you should be knowing something related to super elasticity shape memory. I told you that in all shape memory alloys, you have super elasticity in nature. So irrespective of the load or the temperature you are subjecting, the material will be able to come back to its original position. So this is nothing but the super elasticity nature of any shape memory alloy. So what are the characteristics of it? It is totally an elastic material, totally reversible response it can get to any applied stress. Means to say that material don't have any constraint for load bearing capacity or temperature withstandable capacity. Means it can bear any amount of load subjected or any amount of heat what you are subjecting on that material because it has the capacity to come back, and hence it has a very good elastic response. And that means to say it is very good in having a reversible reaction so that it comes back to its original position. So this is one of the characteristics of super elasticity shape memory alloys. And this nature will come only with respect to the temperature change. If it is at room temperature, if you are not subjecting any heat treatment to it at all, then you cannot exhibit the super elasticity nature in it. So always you have to see that the super elasticity nature comes in the shape memory alloy with respect to the temperature change. So this is the second characteristic of our shape memory alloys. And next is this property always allow our shape memory alloy to bear a large amount of stress without undergoing permanent deformation. This is very important. Most of all the 90% of the material which are available in today's world does not have the capacity to bear the stress to unlimited value, right? It can bear any amount of value. And even though it bears so much of stress, it does not undergo permanent deformation. Why? It does not have the plasticity nature at all. It has super elasticity capability in it. This is the very plus point of this shape memory alloys, which is making the researchers to use this material for n number of applications, because you can use for any temperature condition where the human beings cannot work at high temperature, if you believe or not. That is right? So you can use this materials even for applications at high temperature requirement where even the human being cannot interfere. So without the intervention or without the need of human behavior, these devices can be operated because it can substantiate any amount of high values of temperature without any plastic deformation in it. So this is the very important plus point and the super characteristics of the shape memory alloy. And next important characteristics is the temperature of shape memory alloy is always maintained above the transition temperature. All material will be having a specific transition temperature. Suppose you have a shape memory alloy and its melting point is something around 1800 degrees Celsius. But the phase transition in the shape memory alloys changes within some specific temperature. That depends upon the material what you are selecting. Suppose the copper nickel alloy based, if you take it, so it has a transition temperature at around 200 degrees Celsius first and again at 433 degrees Celsius. So the transition of phase takes place in these two temperatures, and hence the heat treatment what you supply for these shape memory alloys should be focusing on these temperatures so that you can get the required change from austenite to martensite, from martensite to austenite. So phase transition mainly depends upon the transition temperature of the shape memory alloys. So while you do the heat treatment, you should check what are the phase transition temperature of this shape memory alloys before applying the heat treatment. So this is one of the important characteristics. Next one is load is increased until the austenite transforms to martensite. So initially I told you that to get the material deformed, you subject to some mechanical loading, because once it is deformed, then only you supply the heat. So load you have to increase until the austenite transforms to the martensite. You can see this in the hysteresis loop here, right? So this is the austenite. This is the actual structure of arrangement of the molecules in any shape memory alloy. But it has to change to martensite, means to get that twinned deformation in the body, you need some mechanical loading, right? So where, or the temperature. So when you will apply the temperature until which the austenite changes to martensite, or you apply the loading on austenite until the austenite changes to the martensite phase. So that is what being told here. And every material will be having different amount of requirement of either the load or the temperature. It depends upon what is the combination of alloys you are using. So that is one of the characteristics of the shape memory alloy. And next characteristic is when you stop loading, what happens? The martensite transforms back to the austenitic. That is right? So initially you will subject the electrical mechanical loading or the temperature. So that will help you to change from austenite to martensite. But when you stop giving the loading or the heat treatment, it gradually comes back to its original position. So that is what being told as an characteristics of super elastic shape memory alloy. And the last characteristic is the shape memory alloy go back to the original shape as temperature is still above the transition temperature. And it mainly depends upon the type of alloys you're using. Sometimes what happens is the shape memory alloy can come back to original temperature even though the temperature is above the transition temperature. Okay, so means it has the capability of coming down as the temperature starts reducing. For some shape memory alloy, the cooling time might need a very long period to reach back to original position. But for some shape memory alloys, the martensite phase can quickly come back to the austenite phase even before the phase transition temperature has crossed or not. So that shows how elastic the material is. Even without crossing the transition temperature, it can regain back to its original position. So these all claims the super elastic behavior of any given shape memory alloy. And lastly, I'll just tell you about the properties and end up. So these were the super elastic shape memory characteristics. If it comes for the properties, what you can tell is, I told you two families. One is a copper based and the nickel based. So both copper based and nickel based shape memory alloys are considered for n number of engineering materials for different applications. Okay, so all are combined together to develop a novel tailored material for specific devices. So you will play with the copper based alloys, nickel based alloys to see which meets your requirement for specific applications. And these combination of alloys are nowadays manufactured to any shape and size as desired. Sometimes it can be drawn into thin sheets, sometimes it can be drawn into thin wires. It is malleable and ductile both. So it can be manufactured to any shape and size which is desired as per the requirement of the customers or any company or any industries. Third property is the yield strength of the shape memory alloy is always lower than that of the conventional steel. Okay, this is the main property of it. The yield strength ultimately is lower than that of the conventional steel. But some compositions of shape memory alloys have the yield strength more than that of plastic or aluminium material. Even though it is made up of soft shape memory alloys with copper and nickel based one, obviously the yield strength will be lesser than that of steel. But sometimes we can see that the yield strength of these materials are more than even plastic or aluminium. So this is one of the important property. And here I told you that out of copper and nickel based shape memory alloys, nickel titanium based version is used for 90% of the applications because due to many physical characteristics I have told you. So, and hence the yield stress of nickel titanium is being justified here, which can reach until 500 megapascal. So this is the ultimate stress what we can get for nickel based shape memory alloys, which can have the yield stress value of 500 MPa. And one more characteristic is the maximum recoverable strain which comes in this material can hold a permanent damage of around 8% for some alloys. This is mainly speaks about the memory concept of the material. I told you that original position, it cannot come back to 100%. It can be in between 90 to 95. So roughly we can tell the damage which is caused to the material due to non-recovery of the strain is within the range of 8% for some alloys. And this range is not common for all the alloys. For some it can be 2%, some it can be 4%, but majority of the alloys which cannot recover is about 8%. Mean to say that maximum amount of shape memory alloys can regain back its geometry until 92% because 8% of it is damaged due to non-recoverability of the strain in some of the shape memory alloys. And the last property of shape memory alloy is this compares with a maximum strain of 0.5% of conventional steel. Here the things are referred with respect to conventional steel. So conventional steel, I told you that yield strength is comparatively higher in conventional steel in comparison to shape memory alloys. So the amount of maximum strain is of 0.5% of the conventional steel that we are substantiating, because we spoke about the yield stress of nickel titanium and also the amount which cannot be recovered. So based on these two parameters, we are just comparing with that of conventional steel to say that this compares exactly with the maximum strain of 0.5% with respect to conventional steel. So in the next class, we have to speak about experimental phenomenological steps. Okay, so this is just an diagram how it looks for a phenomenological model, but in your syllabus you have an phenomenological experimentation route to synthesize shape memory alloys. So all those things we'll be covering in the next class. So within 5-10 minutes, I'll be sharing today the quiz of yesterday's and today's both together. So you please take care and complete within the tea break, and then you can take the further classes. Any doubts, you're free to ask me now. Mithun?
Yes, ma'am.
Any doubts?
No, ma'am.
Harsha?
No, ma'am.
Sukrut?
No, ma'am.
Okay, and Mohanambal?
No, ma'am. No doubt.
And what about the other, your friends? I think one had messaged that today he cannot come to the class. And about Sandesh? Just ask them to attend the class regularly, or else it will be difficult to understand the concept. Now, everyone kindly type your name and USN in the chat room. Okay, then we will see in the next class. Until then, be safe, take care, and submit the quiz on time. See you all again.
Bye, ma'am.
Yeah, bye bye bye.